Okay, good afternoon, everybody. Here's what I'd like us to try to accomplish today. First of all, take note of this. Exam will be Tuesday. I've decided to go with a paper exam as opposed to the online exam, so bring a Scantron. So it'll be on paper. There'll be about 35 multiple choice questions and worth 70 points, and then some fill in. Fill in means problems to solve, electron configurations to write out, compounds to name, or formulas to write, that sort of stuff. Okay, that'll be on paper. That doesn't mean that it won't be included here as well, but that's where that'll be hit. Chapters 1, 2, and 3. And this was the next topic to do today, and I'm going to postpone this topic. Those of you that did the homework and the quiz, you touched on it. You got involved in this. This is like they're doing the Lewis dot structure of the carbonate ion or sulfur dioxide or sulfur trioxide, and then what is the shape of that molecule? What's the shape of the water molecule? Why is the water molecule bent? That's what this gets into. So what I'm saying is, and we'll look at some study guides and different things for the exam in the last 15, 20 minutes today. But what I'm saying, we're going to postpone this for a couple reasons. Number one, I think we need to finish this and then think about the exam in general. And number two, those of you that are in the 1105 lab, this is what you're going to get to on Tuesday and Wednesday or next week, whenever you have 1105. There's going to be a 2.5-hour lab focused on this. So when I say postpone, what I mean by that, it'll be on exam 2. Okay, this topic will be part of exam 2, but not the exam on Tuesday. All right? So you can kind of put that on the back burner until exam 2. And pay close attention to the lab next week, because I don't even think we won't cover it in any great detail in class. If there's anybody that's not in 1105 lab, you should probably let me know that, because I'm going to be counting on the lab to cover this topic. Okay, follow me? So if you're not in the lab, I will give you some exercises to do outside the lab or talk to you about it. Make sure you get adequately exposed to those concepts. But we won't, it takes about 40 minutes to explain this, and then the lab, that's what your instructor will do. That's what I will do, and most of the other instructors will do is explain it and then give you another 40 minutes to an hour to work out some Lewis structures of different compounds, and then decide what the shape of those compounds would be. And that's the order in which you do it. You decide shape based on Lewis dot structure. All right, so today the main topic we have to finish up with in naming, everything we've said about naming has been focused on ionic compounds. And don't be too concerned here. We don't have as much we have to cover with covalent, but we do have to just show what the subtle difference is between naming those. But to just reiterate here, an ionic compound, typically, generally speaking, you are reacting a metal with a nonmetal. Okay, what is an ionic compound? An ionic compound is made up of ions. Like AlCl3, you've got +3 ions here attracted to -1 ions. The metals tend to lose electrons, and guess what? Nonmetals tend to gain electrons, So that is kind of the perfect situation. Like someone who loves to cook meeting someone who loves to eat. It's a perfect situation. All right? So here's what's happening. Metal and non-metal, you get an ionic compound. Well, what do you get for covalent compounds in contrast to that is typically a non-metal reacting with a non-metal. So that is fairly limiting. We're kind of looking up in this corner. This is where you find the nonmetals. So if you look up in this corner of the table, not necessarily the noble gases, but just right up in here, if you see one of these reacting with one of these, you could kind of your first reaction is that's not an ionic compound. And well, let me just toss a bunch of them out there. Well, you are aware of carbon reacting with oxygen, for example. That's the one you're most aware of. But there is also this. So right away, we can't just call it carbon oxide. All right, carbon oxide. Well, there's a bunch of carbon oxides. There are a bunch of sulfur oxides. There are probably more nitrogen oxides. Okay, so we can't just call them nitrogen oxide, sulfur oxide, carbon oxide. We've got to go to a different way of naming these variety of things that can form when a nonmetal reacts with a nonmetal. And so what we and I shouldn't say, I didn't come up with this. So what chemists have come up with, I made that big, so now how to make it small, is we're going to use these prefixes. All right, we're going to use these prefixes to indicate how many of the different atoms we have in a covalently bound molecule. Keep in mind, when we do talk about covalent compounds, we are almost simultaneously talking about molecules. All right, this is a molecule. This is not a molecule. What's the distinction? This forms an ionic crystal of sodium and chloride ions in a crystal. And so if we heat it up, we don't get NaCl molecules floating out into the atmosphere. They don't do that. But if I have a container of water and I heat it up, actually what actually starts evaporating off the top of that container of water are H2O molecules. They're a distinct little entity, and it's H2O. All right, if we heated up a chunk of salt, it would just get hot. We'd have to heat it up pretty hard to get it to do anything else. So these things are molecules. Some of these things I just wrote there, sulfur, and they are molecules that are telling us what is the composition of that molecule. It's one sulfur and two oxygens. One sulfur, three oxygens. So applying that here, you're familiar with that, carbon dioxide. We're just using that prefix. Carbon monoxide. So you can see in that one, we don't necessarily apply the mono to the first atom. If there's only one of them, we carbon monoxide, but the second one we do say. So there is sulfur dioxide. Well, this one proves a little point. Carbon, so we don't say it's monoxide, it's monoxide. Starting to try it. Monoxide, so we don't, if there's two vowels next to each other, generally, not always, generally we drop one of them. So carbon monoxide, carbon dioxide, sulfur trioxide. Now, if we get into an example like that, Na2O5, we are going to say how many nitrogens and how many oxygens. So it's going to be dinitrogen. What's the prefix for 5? Pent. Penta, but we'll say pentoxide. Since there's an A and an O, that would be pentoxide, would drop the A and call it pentoxide. Dinitrogen pentoxide. All right, so here's how we're piecing them together. We're still the second atom in there, the most electronegative atom in there, is generally going to change over to the IDE ending. All right, so help me out here. What is this? Silicon dioxide. See the silicon right below the carbon, it's up in this corner here. Actually, along here were metalloids. Metalloids, we say they can act like a metal or a non-metal. If it reacts with, like oxygen right over in here, it's a non-metal. So it's in the non-metal. It's very close to the element that it's reacted with. Silicon dioxide, we just did this one. Dinitrogen pentoxide. What about this one? Now that's not an I there. That's not, keep in mind here, that's not iodine. That's a Cl. Okay, that can be a little confusing sometimes. So think, well, that's a carbon, now I got another carbon and an iodine. No, that's a carbon and a chlorine. So what do we call this one? Carbon tetrachloride. So that's the tetra. Anybody know what that used to be used for? Carbon tetrachloride. It was phased out probably 30, 40 years ago now. You went into a dry cleaners. Well, you go into a dry cleaners today, and you do detect an odor of some sort. It's the solvent they're using. All they mean by dry cleaning is it's not getting wet. It's not getting wet with water. It is getting wet with some organic compound. Used to be that one, carbon tetrachloride. But it was determined to be carcinogenic, so the people that were operating in these dry cleaners were being, pretty much bathed in a carcinogen pretty routinely. So it was banned in, I think, the 70s. I'm not exactly sure when, but that's carbon tetrachloride. And so that was dry cleaning fluid. All right, here's one that gets us to use one of those really high prefixes. So this is iodine. Iodine, what do we want to call that one? Iodine. Heptachloride. Fluoride, excuse me. Fluoride. Now, one that I worked somewhat with when I was at Dow Corning and working on silicones, that this wasn't our most favorite compound, but you can see it's got the similar formula as this right here. It's right underneath carbon, but actually behaves quite differently. So what would you call that? Silicon tetrachloride, silicon tetrachloride. And so here's carbon tetrachloride. To a chemist, if you said, oh, we need a little carbon tet, they wouldn't say anymore. That more or less know you're talking about silicon tetrachloride. We're going to react this with carbon tet. This is not soluble in water, very dense. If you drop that into water, it would drop to the bottom. Where gasoline floats on top of water, carbon tetrachloride will sink to the bottom of water. It's an organic compound, carbon-based compound. This one will react with water immediately. As a matter of fact, if you had a bottle of silicon tetrachloride and just took the top off the bottle, you would see HCl fumes coming out of the bottle. Just the humidity in the air would react with that very rapidly and form HCl gas. So it's very, very reactive with water. You couldn't, you drop that in the water, it would just completely convert to SiO2. It would convert to SiO2 and HCl gas. That would be the result. We'll write, not today, when we get to chapter 4, we're going to start writing chemical reactions and balancing chemical reactions. And so we're building this house, foundation, walls. Pretty soon we'll put the roof on this thing and you'll be chemists. You'll be walking out of here at finals day, an official chemist, all right? At least you can talk like one, act like one, all right? No one should be able to pull the wool over your eyes when it comes to chemicals. All right, just to mention a few things here that are so common that we don't use the nomenclature. We just use their common name, like water, H2O. We don't call it dihydrogen oxide. We call it water. NH3 is ammonia. We'll see here in a minute. For some of these carbon-based compounds, you need to take chemistry 1307 because the first 8 weeks is organic chemistry. And I'll point out a couple things on our worksheet here that are kind of sending you down the wrong path. I'll point those out in a second. Because organic compounds have their own nomenclature system, the IUPAC system of naming organic compounds. So they're in a huge class all by themselves because there are literally tens of thousands of carbon-based compounds, organic compounds. So they have their own way of being named, and that's a big chunk of chemistry 1307. What are these different classes of organic compounds and how are they named? So let's see, what do we got next here? Okay, so take out this worksheet. Take out this worksheet. Remember I told you to ignore this bottom chart. Let's not ignore it. Let's do that together. We'll just do that chart and the one at the bottom of the next page together. Yeah, does anybody else need one of these? Here you go. Everybody have one? You're welcome. Okay, so we're looking at the chart at the bottom, the set of tables at the bottom. So we have N2O3, so there's dinitrogen trioxide. Oh, now notice there, it's saying molecular compounds, nonmetal plus nonmetal. Or you could write underneath there, covalent. What holds a molecule together? Covalent bonds hold it together. They are sharing electrons. So we could essentially use those words interchangeably. A molecular compound is a covalently bound compound. And so number 1, we have SF6. So what is that? Sulfur hexafluoride. Number 2. Okay, we got carbon monoxide over there. Carbon monoxide. Just carbon monoxide. If there's nothing in front of it, assume there's one of them. Assume one. So we just have carbon, no prefix. So there's one carbon. But we're saying how many oxygens because it can have different numbers of oxygen. Okay, number 3. Number 3, this is Chem 1307. Okay, that is not dicarbon hexahydride. Forget that. That is ethane. How do you know that? Because I just told you. All right? That doesn't fit our system. This is the IUPAC way of naming compounds. So don't get hung up. And there's one on this other chart too. So now let's turn over to the chart at the bottom of the second page. Again, it says molecular compounds. And we got another 1, 2, 3. ICL. What is that? Iodine. Iodine what? Mono. We are going to throw the mono in there because there might be an ICL3 or an ICL7. Let's assume there is some other iodine chloride ratio. So we'll call it iodine monochloride. For the second one, do use a prefix. Number 2, we've done that one, dinitrogen pentoxide. We did it from the formula, we named it. Now you have a name, and you need to convert that into a formula. Now, before we just gloss over this real quickly, keep in mind that when you read something like this, dinitrogen pentoxide, it's kind of giving you a clue that it is a molecular compound. That's not ionic compound naming protocol right there. That is the way we would name a covalent compound, and that's what it is. We've got nitrogen and oxygen. They're sitting right next to each other. So what's the formula for that? What's the di stand for? 2. The oxide stands for oxygen. Pent, 5. Okay? So there you are, you're translating a name into a formula. Now here is a compound being made up of two halogens. We've got bromine and fluorine. Bromine trifluoride. Oh, it's a 5. I'm sorry. I looked at it. I thought I saw a 3 there. I'm sorry. I thought that was a BRF3. It's a BRF5. Pentafluoride. So here we are keeping the A in the penta. Now the fourth one is just wrong. Okay, just cross that out. Tricarbon octahydride. It is going to be that. I mean, I could write this from that name, but that's just a crazy way to try to name that molecule. That molecule is called propane. Propane. And if you were in 1307, I mean, you would learn that the second day you were in that class. 3 carbons, saturated hydrocarbon like that, 3 carbons, propane. Propane. Yeah, the little white cylinders underneath your grill. That's what's in it. If you went to Lowe's and asked them for some tricarbon octahydride, they'd probably call the manager and say, we got a really strange customer on here. I don't know where they're from. From the moon. They would have never, ever heard propane called that, okay? If you said that, if you went down to one of my colleagues and asked them for some tricarbon octahydride. So here I am, apologize. I handed this out to you, so cross that off there. I went back to my office and got that off of there for any future. I don't know why I didn't notice it sooner. Okay, so just cross that out. That's not a way to name organic compounds. Would you come to that name if I gave you that formula? Yes. That's what, I mean, what else could you do? You have to scratch your head and try to guess, right? But I won't give you organic compounds. Try not to. All right, now, if you have any questions on these, but let's take a look back over here now. The last page, you've got 2, 4, 6, 8, 10. You've got 10 formulas, and you're asked to give the name. And then what do you have? You have 10 names. You're asked to give the formulas. So number 1, the top part of that, A through F, are ionic. If you look at the top, those A through F, you've got a metal and a non-metal, sodium and fluorine. You can see, you got a metal and a non-metal. Manganese and oxygen, metals and non-metals. So those are generally ionic. But then if you look at G, H, I, and J, you got Pi3. It's phosphorus and iodine over here. Sulfur and bromine right next to each other, diagonally. Iodine and bromine right on top of each other. And xenon and fluorine. So those are all you're going to want to give them covalent names. Name them in the covalent system. I wouldn't worry too much about C or D. Yeah, I wouldn't worry too much about those, but first one is NAF. That's pretty simple. What do we got there? Okay, what I'm saying here, you're not going to call this sodium monofluoride. You don't need to call it sodium monofluoride. It's an ionic compound. It's simply what? Sodium fluoride. Just like you would name sodium chloride, sodium bromide. All right? So that's why I'm saying you have to kind of get in your mind, what am I talking about, an ionic? And I name it ionically. And then when I get down to something like G, and I have a Pi3, that's not going to be phosphorus iodide. It could be. Could be, but we got a non-metal reacting with a non-metal. So phosphorus yeah. That's a no. That's not, because see, if we looked at that as an ionic compound, what would we be looking at? We would say, okay, phosphorus normally has a -3 charge. And iodine normally has a -1 charge. So we don't have a positive ion attracted to a negative ion. We're talking about two negative ions. So they're not going to transfer electrons, they're going to share them. Okay? So it's not going to be phosphorus iodide, because this isn't a +3 ion. It's a -3 ion. It's a nonmetal. So they're going to share. IO died. There we go. Is that right? And here is one, and if you Google that, it would come out phosphorus triiodide. It would actually keep the two I's. Triiodide. Yeah. Keeps the two I's. Here's one case where they patterned it after my name, which has 3 vowels right in a row. They decided to keep 3 vowels right in a row. I don't know why they did that. Sometimes it has to do with punctuation. Okay, but this is a nonmetal. Phosphorus is a nonmetal combining with a nonmetal. That's what's leading me to this. I'm not just going to call it phosphorus iodide. All right, so G, H, I, and J are all would be named by the covalent naming system. Now let's look at number 2 below there, because and again, A through F, is that right? A through F are ionic, and G through J are covalent. All right, so this gives you a little bit of practice in, okay, how do I name this as an ionic compound? And then, okay, how would I name these others as a covalent compound? G through J, notice that you're seeing the prefixes. Hexa, tri, di, penta, okay? That's kind of a signal. This is a covalent molecule. Don't use those prefixes. This is one of the things that students sometimes see. They start bringing these prefixes into ionic compounds. So, you know, they would come up with something like this: magnesium dichloride. We don't call that magnesium dichloride. We say we know that's a +2 ion. We know this is a -1 ion, so we are going to name it in our ionic nomenclature. We just say the metal ion and the name of the anion, the chloride. We get magnesium chloride. All right, so I'm going to do some of the easier ones just real quickly. Barium iodide. All right, now this one is worth concentrating on for a second here. Why? Palladium. Other than going to the movies, out at what is it, the Rim, or where's the Palladium? Out at the Rim? Sometimes I get the Rim mixed up with some other place. But okay, other than that, this is kind of an element we've hardly mentioned, palladium. But you see a Roman numeral 2 after it. So what is that telling you about the palladium there? It's charged. What charge does it have? +2 charge. All right? So here you are, you're faced with something you've never seen before, but all of a sudden, you know that it has that chemical symbol. You can look at that on your periodic table and find palladium. And because of this, you know it has a +2 charge. And you already know what bromide is. What charge does it have? -1. Okay, so right there you're equipped with enough to figure out what the formula of this is. So the 2 is going to come over here, and we're going to get palladium bromide. Palladium 2 bromide. That would also suggest to you that there's another palladium ion. It might be a 3, it might be a 4. You don't know what it is. But because they're using the Roman numeral, it's signaling to you that there's another palladium out there with a different charge, just like with iron. It has +2, +3. Palladium might be +2, +3. Zinc arsenide. Zinc arsenide. Nitride, phosphide, arsenide. Arsenide. That's a toughie because that's a little bit tough because it goes zinc, Can it have more than one charge? There's no Roman numeral there, and then zinc is almost always a +2. So let's skip over that one because you might not know enough to deal with that. Let's do D. I'll tell you what. Let's get D in here. Let's erase that. Put D, so we have gold. Let's not ignore gold. Gold 3 oxide. Okay, do that one. Figure that one out. Gold 3 oxide. Okay, it's just like the palladium 2 bromide. Here's gold. You know, you're familiar with gold, but you haven't done anything with formulas. The 3 is telling you it has what charge? +3 charge. Oxide is always -2. All right. Au2O3, gold 3 oxide. Copper 1 sulfide, lead 4 oxide. I'll leave some of those there for you. Well, let's just do G. What's the formula for G? Okay, sulfur hexafluoride. Give me the name, write me the name of this compound. Okay, write out the name for that. Fe2SO43. What is it? Iron 3 sulfate. All right. I'm kind of baiting you there. I was seeing whether we would get the 3 in that name. That name needs a 3 in it. And how do you know that? You know that because I've told you iron can have 2 different charges. Because, for example, I could have said, okay, name that compound. Those are both iron sulfate compounds. They both exist. We can buy a bottle of each of those. We might even have a bottle of each of those over there. For all I know, we probably do. Iron sulfate. So we have to distinguish them. This has a -2 charge, that has a +2 charge. How do I know that's a +2 iron? Because I only have one sulfate with it. Okay? So that tells me that has to be a +2 iron. So this is iron 2 sulfate. And that's iron 3 sulfate. Now, you can see that I am emphasizing this. I'm putting a lot of attention on the right name, the right formula for these compounds. It will be next Thursday, the class after the test, that we really come back to this and you see why it is so important. Can't get there yet, but we're going to be there next Thursday. Just trust me right now, this is a skill we have to proceed accurately with writing chemical equations, finishing chemical reactions, and lots of other things that have to do with it. So that's just why it's emphasized. And why chemists are so particular about names and formulas, and the right formulas, okay? Okay, so that covers pretty well the naming. Remember, we got those practice quizzes. I'll get to that. I'm going to go back to another slide, and where is it? I should have remembered what slide number it was. It's the one, electronegativities. Where did we get to electronegativities? There we go. This one and the next one. Okay, we've already covered this, but I just want to, let's say, so you got this scale. Boy, I've written all over this thing. You have this scale right now that shows you where we have the boundary line, or where we stop talking about it being just covalent and start discussing it as a polar covalent molecule and then an ionic molecule. Just know that even from here to here, the bigger the difference, the more ionic in nature is the compound, the bigger the difference. So let's take, let me ask you a question here. I'll keep that right up there. So there's our map. You need to know this, okay? That's not being given to you on the periodic table. You kind of need to know this. And what are we looking at? We're looking at the difference in electronegativity. So I can't hold up everything at the same time. So why don't you take these out and have this available right now. That's your electronegativity, your chart of electronegativities. That's the only thing that's on there. That information does not appear on the periodic table, okay? We don't have the electronegativities on there. We've got atomic number, average atomic mass, and symbol. This is just showing you what are the electronegativity values. So what if I were to ask you, which of the following what is Ga? That's gallium. Okay, let's, which of the following is ionic, or maybe, yeah, is an ionic compound? So I'm going to give you rubidium chloride versus gallium bromide. Which of these is ionic? How would you answer that question? You know, based on this difference in electronegativity. All right, so chlorine is 3.0. Rubidium is what, 0.8? Bromine is 2.8, and gallium is 1.6. All right? So which one of these is ionic? The rubidium chloride. It has the higher, the greater difference in electronegativity. We very clearly have a metal with a non-metal. Over here, yeah, you might say that's a metal and there's a non-metal, but their difference is only 1.2. So what kind of bond, what kind of chemical bond would we say is in the gallium bromide? Polar covalent bond. This is a polar covalent bond. It sits right in here. All right, it's got a 1.2 difference, so it's right in that range, like water, of being a polar covalent bond. All right, so if you ask questions about what type of bond would be in this compound, or which of the following compounds is most likely to be ionic, if it says that, most likely to be ionic, well, find out which compound has the greatest electronegativity difference. I mean, even if you had two that came up if one came up at 2.0 and another one came up at 2.3 difference, this is the one that's is more ionic in nature than even a 2.0. Greater the electronegativity difference, the greater ionic character is in that bonding and that compound. All right, so be aware of this, how to use this scale of electronegativity differences to predict what kind of bonding is there. And we said that, you know, we basically have covalent bonds, covalent ionic, but in the covalent region, we are saying there are covalent bonds where the electrons are shared fairly equally, and there are covalent molecules where the electrons are shared unequally, and you get a polar bond, like water. Like water. It is covalently bond, it is molecular, but it has a polar character to it. Okay, so in chapter 3, you should be able to relate to the type of bonding that's associated with a particular compound. All right, now let me stop there. I think we've covered what I want to cover. Like I said, I'm postponing this. I don't know what pages that is in chapter 3, but towards the end of chapter 3, there's probably 6 or 8 pages that deals with Lewis structures and molecular geometry, which you can kind of gloss over in terms of preparing for this exam, and then focus on it after next week. All right. At this point, I can go on to Canvas and just point out a couple of the study guides that are there, and then just quickly pan through chapters 1, 2, and 3 in terms of what have we covered, and then answer any particular questions you might have. So, okay, if you go here to study guides, just look at the study guides, and there's lots of them, but they're kind of broken up according to exam 1, chapters 1, 2, and 3. Chapters 1, 2, and 3 here. So you've got a study guide, and then this one has the answers. So this has all those questions plus the answers. My recommendation is to try to muscle through this without the answers first. That's where the neurons are making their connections, when you muscle through it, okay? You got to work to get those neurons to grasp this new information, and then you can go check your answers. So you have this, chapter 2, summary outline. I don't know what that is, but you can take a look at all that stuff. There's practice problems from the back of the book. The problem with these is this is probably based off of the 8th edition and not the 9th edition. And what McGraw-Hill does is sometimes they put the same questions in there, just change the numbers so that you can't. So you got to buy a new book, things like that. So if that's maybe not as helpful. Now, there's some down here that you might ignore until the final exam. But for example, right here, I'd have to see what all these are. But let's take a look at what this is. And let's look at that. It's the final exam study guide for chapters 1 through 8. So let's open that up and look at chapters 1, 2, and 3. And basically all that's doing, what that study guide is doing, is just reminding you what were the key concepts in each one of these chapters. Okay, so open this up a little bit more. rounding, significant figures, conversions between English and metric system, conversions within the metric system. So learn to convert grams and milligrams to kilograms, meters to centimeters to kilometers, liters, milliliters, kiloliters. Scientific notation, density and temperature. All right, and remember on density, there are 3 types of problems. Somehow I can't write. I don't know. When I'm on Canvas, I can't write on my screen. I don't know what's. Remember, that's the equation, and if you translate that over here in that configuration, then if you want to calculate density, you need mass over volume. And if you are being asked to calculate volume, it's mass over density. And if the mass is the unknown, you know the density and the volume, you can determine the mass by multiplying those two, all right? You can do it algebraically, you can do it off of that. But if you remember this triangle wrong, it'll be wrong, okay? The algebra, if you remember your algebra correctly, you can go to this algebraically. So that's kind of why I like algebra. Chapter 2. So atomic theory, structure of the atom, the principal particles of the atom, energy levels, sublevels, what the capacity of those sublevels are. This is the capacity. That should probably say S sublevel. The P sublevels. P sublevel. Yeah, I should probably change that. That should say sublevel. There are 3 p orbitals, and they hold 6 electrons. Atomic number, atomic weight, electron configuration of the atom and also of an ion. You should be able to do the electronic configuration of an ion. If I said, what's the electronic configuration of the Al plus 3 ion? You should be able to do that. Do the atom, and then strip out the 3 valence electrons. And you got the ion. Yes, Jennifer? Is that a yes, or is that a, that sounds familiar? Does it sound familiar? Okay. All right. Well, what I don't have listed here is how you calculate that number. That should be listed there. Average atomic mass. Remember, we got that from the chlorine 37 ion and the chlorine 35 ion. The relative abundances. What does a chlorine 37 ion weigh? That's given to you. What does a chlorine 35 ion, or isotope, not ion, isotope. What does the chlorine 37 isotope weigh? Chlorine 35 isotope weigh? And then the relative abundances. And here's where we're concentrating on the mass number. We want to know how much does this isotope weigh? And let's say I said it weighed that many atomic mass units, and it was that's the relative abundance, and that this one weighed and its relative abundance, let me see, that's going to be 75.04%. Is that right? Does that add up to 100? I think so. Yeah. 96 and 4 is 1. Yeah, that'd be 100%. All right? And remember, you convert this to a fraction, to a decimal, and multiply it by this and get that average atomic mass. So be able to do that calculation. It won't be chlorine. Right? It won't be chlorine that's on the exam. But if you're given the two isotopes, what they weigh and what their relative abundance is, you should be able to convert that to this number. And I may not be looking for the number that's right on your periodic table. Okay, so don't just think, oh, I can go to the periodic table and just write that number down. I want the number that you get from the data I give you. Okay, now what you can skip here is the Lewis dot diagrams of atoms. Well, the atoms is appropriate, but the molecules and polyatomic ions, that's what you can skip. So, for example, the Lewis dot diagram of phosphorus. How do I know that? That's group 5A. And let's see, what group numbers do I have on here? All right, go off of these. See these group numbers? You got a 1 and a 1A, a 2, a 2A. Over here you got a 13, but you got a 3A. 3A, 4A. That's where you're getting the valence electrons off of that. 3A, 4A, 5A up to 8A group number on your periodic table. And I have one of these laminated like this for each one of you. All right? I just want you to know, you don't bring yours in. Don't rely on everything you've scratched down on yours. Okay? This is what you'll be given. Everybody has this. Questions? I didn't go over all of this here, but I just wanted to tell you, you don't need to worry about geometry, and you don't need to worry about the Lewis dot structures of molecules and polyatomic ions. But naming, all of that. I do have office hours Tuesday morning, I think from about 9:30 to 11, and then a lab, and then your exam. So bring a Scantron, bring a calculator, Scantron and a calculator. No questions? Okay. Very good. I've got to go to the dentist, so I'm in no hurry.